The AP exam doesn't specifically expect that you would know the terms precision and accuracy relative to lab experiments, but it does expect that you can analyze experiments and compare the results of various trials and data. And this is where the terms precision and accuracy can come in. You have to memorize those terms. Knowing what they mean is important. So let's look at this experiment. We're doing an experiment to find the density of water. Now, this is nice in an experiment where you know what the correct answer is. In this case, it's the accepted value at 25 degrees Celsius is 0.99705 grams per ml. I mean, this is an unbelievable level of accuracy. To measure it this accurately, you'd have to take into account the buoyancy factors in air, because the air would actually change this density slightly because the water is sort of being buoyed up by the atmosphere around it. But let's look at these experiments. Here we've got experiment 1 and 2. And as you can see, they've got the density down to 1/10 of a gram. To do an experiment like this, probably you'd be using a standard high school lab and maybe even some college labs where you'd have a balance, in this case, go to 1/10 of a gram, a graduate cylinder, you'd be measuring 20-30 mLs of a liquid. And if you know the mass of the graduate cylinder and the volume of the liquid in it that you could estimate using a graduate cylinder, and of course the mass of the liquid and the mass, you could do a density calculation, which I'm not going to get into. In this experiment 1 that they're doing, they find a density of 1.0, pretty close to the expected answer, 0.997, but this is as good as you could get with that balance. And then a value that's a little bit higher than the accepted, one that's a bit lower than is expected. One of the ways in which we can analyze this is this classic dartboard analogy, where you have a dartboard where you've got an expected answer. In this case, the expected answer is 0.9975. And you get some answers that are close, some above 1.1, some below 0.9, and some that are pretty close to what you'd expect the answer for. If you were to average these values that are a little bit disparate, they're off by, there's a variance of 0.2 grams for this, grams per ml, you would find out that if you average these, you get an answer that's 1.0, which is about as good as you can get with this type of experiment. You classify the answer as being accurate. You're close to the right answer. That's what this idea of accuracy is. But it's imprecise in that the data is sort of scattered a bit in this arrangement. Now, in this experiment, you're going to see that we've got, again, things, in this case, down to 1/100th of a gram per ml, but the answers are 0.9, which is lower than you'd expect, 0.79 lower, 0.5 lower, but way lower, and 0.7. And again, with our dartboard analogy, you'd say, whoa, in this case, if you average them, you get a density of 0.73, much lower than the accepted value. And the dartboard analogy is here that you're not even close to the right answer. And on top of it all, your data is scattered everywhere. If this were a student's experiment, I'd say, I don't know what you're doing wrong. Do you know how to read a graduate cylinder? So this would be neither precise nor accurate. And the idea of an experiment is, okay, any experiment's got some latitude, and you'd like the average to be close to the right answer. And if your average, in the case of experiment 1, the student is doing the best with what they have. Now here are another set of experiments, experiment 3 and 4. We're dealing with 1/10 of a milligram, gram per ml, which is 4 significant digits if you know about significant figures. And that means you've got some equipment that is more expensive. If you're doing this, you might be using a device like this, which would be a specific gravity bottle where you've got a thermometer and you've got a temperature that's accurate and you've got a volume that's extremely accurate, and you're paying $371 to be able to do that. Another less expensive method that's a little bit harder to deal with is these little things, the unpronounceable pycnometer, where you have a bottle that you can get an extremely accurate volume with because it's got a thin capillary. So when you fill it, you know it's exactly there. you're not judging like a graduate cylinder, and you can use a very accurate balance, and this will get you some very, very decent density measurements, but this takes quite a bit of while. You better expect to spend 3-4 hours in a lab to be able to do this type of experiment when you get these accurate volumes and measurements. But back to our data here. In this experiment, we have material or results that are pretty close together compared to these other experiments. So we've got quite a bit of precision. There's not much variance. 3, 4, 3, 3, 3, 4, 3, 3. These are grouped together and you say, hey, this experiment's going nicely, but the value is way off. So our dartboard analogy is, hey, precise. They're getting everything's right down. I mean, these darts are close together. These measurements are close together, but they're not close to the answer. In this case, I would say that something's wrong with the water that you've got. You're probably measuring maybe some water that's contaminated with some alcohol, so its density is too low. Or one of your measurements, like maybe the measurement of the empty pinkometer is incorrect, and that is throwing everything off the same amount. In other words, you're making a consistent error rather than here where your errors are all over the place. So this is one thing that you should be able to see in an experiment. If the question that you had on data was, what's going on here? You say, well, there's a consistent error. And I think, like I say, if the water that they're measuring the density of is not pure water, that would explain it. Or if one of their earlier measurements was incorrect, and that measurement is being used in all of these calculations. Now, let's look at our last experiment here, where we've got, if this is the right answer, this is as good as you can get. This is as close using the device that you've had, that pinkometer or that specific gravity bottle. And the dartboard analogy is precise and accurate in the comparison of these. So this is a very, very nice experiment, 0.9970, bordering on the limits of measurement for a density of a liquid. This type of experiment is done, like I said, with a pinkometer, but that's old school. The modern method of measuring densities with accuracies that high. And those accuracies sometimes are worth doing. If you've got a quality control for a material that you're selling, let's say you're selling orange juice or Coca-Cola, and you want to make sure that the amount of sugar in it is right, or you've got a wine and you want to know the exact density, then probably you're going to be looking for one of these things. This is a Mettler device, and you're dealing with something that's in the range of $12,000. In fact, you don't use gravity. Gravity and balances are a little bit tricky. In this case, rather than using volume and mass, they measure the oscillation of a liquid. They produce a little vibration, and from that oscillation, there's some calculations you can do to get a density measurement very, very quickly and consistently. If you want to see one of these things used, check out a YouTube for a Mettler Toledo Easy Plus Density Meter, and they'll show you some neat experiments that are done using this quality $12,000 instrument. If you're working in a lab with one of these, you're working at a top level lab. Okay, there we go. Precision and accuracy. Again, you don't have to memorize the terms, but you should be able to see experiments to see if their data is consistent and to the level of accuracy because they have a greater number of significant figures. All right, that's our explanation.